Hey folks, welcome to the Webinar Wednesday presentation on designing an overmolded part with SOLIDWORKS Plastics. My name is Damon Tordini. I'm the product manager for plastics and flow simulation here at Hawkridge Systems. And specifically what I want to talk about in this presentation is how SOLIDWORKS Plastics can work with the SOLIDWORKS 3D modeling design tools to help you make the right decisions when you're creating an insert overmolded part. And specifically, we're talking about that type of injection molding and manufacturing. The idea being that if you simulate some of the manufacturing processes in SOLIDWORKS Plastics, you can see what the right design decisions are that you could make up front to create a part that not only operates the correct way in the real world, but has high quality and can be manufactured in the best way, cheapest way possible. So insert overmolding, if you're not familiar, is a manufacturing process that combines injection molding with some other existing type of materials to create a more complex part that does maybe a more sophisticated task. Traditionally, it works by taking either a metal or a plastic piece of material that's been manufactured some other way and putting that so-called insert into the cavity of an injection mold and then injecting molten plastic around it, ideally bonding the two materials together and creating a part that's made out of two different substances. So this is useful for things like connectors, where you need electrical conduction through some metal parts in the component, or maybe a part that has one plastic that's stronger than another one for a different kind of surface finish, things like that. And of course, there are always traditional guidelines and design rules that you can follow in any injection molded part design. For example, trying to maximize the amount of surface area or area of contact, between the parts. But there are a lot of other effects of any design change that maybe aren't covered by these rules. And we need a software to more specifically tell us what that effect is, what will happen if we make that change, and whether it harms or helps our cause. And so injection molding software, in general, of course, can simulate what the filling and packing and cooling phase of that cycle looks like, and tell you, roughly what the quality of the part will be, and if there are changes you could make to the material or to the gate location, to get a more easily manufactured part and higher quality part. And so insert overmolding is one of the capabilities that SOLIDWORKS Plastics has to simulate that part of the manufacturing process. And typically the important things there are to try to make sure that the materials have bonded properly and aren't going to fail or separate, which largely has to do with the heat transfer between the two different materials. So let's take a look at how we can do that. Of course, you're probably aware that we offer a pretty wide variety of products and services at Hawkridge Systems. And on the simulation or analysis side, we have both SOLIDWORKS simulation tools as well as more advanced kind of higher end analyst tools such as Simulia Abacus. So we're basically referring to the validation and simulation part of what we can provide here. And specifically, you may be familiar with some of the SOLIDWORKS simulation tools like the stress analysis in SOLIDWORKS Simulation Standard, or maybe things like drop test or even nonlinear analysis. Those would be under the SOLIDWORKS simulation package. And we also have SOLIDWORKS flow simulation, which would do things like thermal analysis or maybe simulate liquids through a manifold. SOLIDWORKS Plastics is a separate license which can be purchased on its own, which is a very specific tool. It's meant for one thing only, which is simulating the manufacturing process of injection molding. So that's the tool that we're going to be looking at primarily today to help make these types of decisions, to figure out how high the quality of these parts are going to be, how easy it is to manufacture them, maybe how expensive it will be to manufacture them. So SOLIDWORKS Plastics can do this because it has a large database of not only plastic materials, but actually metals as well, which, as you'll see, will be important for insert overmolding. And it allows us to simulate the injection of the molten plastic into the cavity of the mold without actually needing to model the mold, and getting a huge variety of results which can predict whether it's even possible to fill this part, how long it will take, if there are going to be any quality issues that we need to be aware of. And we can do this not just for simple parts, but for more complex types of injection molding such as co-injection of multiple materials, insert overmolding, different kinds of materials like thermosets or rubbery materials. And because this is all integrated into SOLIDWORKS, it's pretty easy to learn, and it also makes it as convenient as possible for checking the effect of these design changes that you're probably already making in SOLIDWORKS. So let's take a look at what the process looks like to go from just a simple part model to some analysis results that can give us more feedback on our design. Of course, we're talking about the capability of SOLIDWORKS Plastics here, and you should be aware that they're split up into 3 packages. Plastic Standard being more for just a simple fill check of a part that would be done by maybe just a part designer that doesn't really have any knowledge or input on the mold setup. Plastics Professional, which is the middle package there, would be the minimum level of the software required to do any of these kinds of simulation with insert overmolding, being able to specify that there's an existing insert of a different material in the mold. So I'm going to open up SOLIDWORKS. In this case, it's 2017 here, the current version of SOLIDWORKS. And I've got a part file that you can see here that I've modeled up. I've actually modified this a little bit from an existing model, and it's a simple 5-pin electrical connector. This is the male side. And what we got on the screen right now is actually the final product, which is really just 2 parts. It's the electrical connector plus sort of a rubber sleeve on there. So I'm going to switch to a different configuration that has the electrical connection only, just a plug. And that's, of course, because in injection molding, we traditionally manufacture one part at a time. Right? We wouldn't injection mold things in their assembled state or anything like that. Of course, you might have a multi-cavity mold, which does do more than one part. In this case, though, we are going to treat this as a simple one-cavity mold. And so you can see here, if I take a look at the feature tree, this is a simple part file. And the way I've modeled it, I sort of started by modeling the plastic volume of the part, the part that would be injection molded. And there are some cavities that I cut out of that with some simple cut revolve features there. And that, of course, is where the electrical pins would be in place in this situation. And the injection molded plastic would have actually flowed around that. So really all I would need to do as far as modeling the part at the beginning here is make sure that these are separate solid bodies in my part file. You can see right here I've got the socket itself modeled up. And then here if I roll down the feature tree, I've created some revolved bosses and then patterned it around. And I've just made sure that in the revolve feature I didn't check merge result. That's what's giving me a multi-body part right now, which if you go to the top of the feature tree, you can see listed here under the solid bodies folder. And so because I've modeled these as separate solid bodies, SOLIDWORKS Plastics is going to recognize that and allow me to specify that they are made of different materials, and I'll be able to simulate the flow of the molten plastic around those existing metal pins. And of course, I want to do everything from see what kind of pressures and time are required to fill that, and maybe what the temperatures are in the cross-section there to evaluate if the materials have bonded together well. And of course, I can do things like check what the surface area is between those different materials, which is part of the kind of equation here for how well the mechanical bond will have worked. For example, I could select the surface area or the faces of these holes and use the measure tool to see what that surface area is. But that's really not enough information. If I injected my plastic material at different temperatures, or if I used a completely different plastic, or I used different pressures, all of those things would have a big effect on the heat transfer. So that's where the simulation is going to give me much more information than just following the traditional rule of thumb. So what I can do here is go to my add-ins tab and turn on SOLIDWORKS Plastics. That's going to enable those injection molding simulation capabilities. So here I'm going to start by using the Getting Started wizard, which is going to take me through the key steps in setting up a new simulation and help me not forget all the basic things that are required for every analysis. And if I look on the right-hand side of the screen here, the first step is to generate a mesh. Like most simulation tools, we have to take the solid geometry that we've created in SOLIDWORKS and split that up into some discrete elements, individual pieces, that have some known equations in them, and then the simulation will figure out what the velocity and temperature and pressure of the molten plastic is in all these elements as the manufacturing process is happening, of course. And so there's always a trade-off between the detail in the mesh, the size of the element, and how long it's going to take for the calculation to run. And that's one of the key choices to make here. So this wizard on the left-hand side is going to pop up. And the main thing that's important here when you're talking about insert overmolding is specifying the right domain type for the individual bodies. You can see that because I've modeled the pins, those are 5 separate solid bodies, they're showing in the list. But they're not going to be part of the cavity. The cavity would be the empty space that the molten plastic flows into. So instead, I need to select those bodies, change the type to insert, and hit apply. And now SOLIDWORKS Plastics will recognize that those are going to be different bodies, existing bodies that were placed into the cavity of the mold. I'm going to be able to put different materials on those, like let's say copper or brass, which is going to have different thermal conductivity and other physical properties, and will give me a more realistic simulation of the flow of the molten plastic and the heat transfer between those different materials, and help me estimate if they have bonded correctly. If I hadn't included the inserts in the part here and simply left them as empty holes, Plastics would have treated that as basically being part of the mold. And as you can imagine, the thermal properties of a copper insert are very different than just assuming we've got steel in a mold at a fixed temperature. So what we need to do here is plug in some mesh settings. We could use the default triangle size, of course, or we could change it. And what's most important is that SOLIDWORKS Plastics lets us use what's called automatic refinement, where I can plug in a sort of a tolerance value here and choose how smoothly I want the mesh to refine itself in different areas. And that will visualize automatically for me where the smaller features are, more detailed features are in this part, and reduce the element size appropriately. You can see that it's added in a lot more elements around these pins to properly capture their circular shape more effectively. So I can proceed here through the rest of the meshing wizard, where now I've got this surface mesh generated, the surface triangles, and I can fill in the volume of the part with what we call a tetrahedral mesh. And specifically, this is a hybrid tetrahedral mesh. And what that means is when I click Create Mesh here, it's going to fill in the solid volume with tetrahedrons, which is sort of a triangular pyramid shape, but also use a special, what we call sort of boundary layer element near the surface. And those are much thinner and ensure that we get good results near the walls of the injection mold. So now we can visualize this sort of a cross section of the part and insert. That's going to be important for calculating the temperatures accurately. And we can proceed to simply finishing the wizard here. So now that that's done, we'll have an idea of how long the simulation is going to take to complete. In this case, it's 130,000 elements, whereas in plastics, with a normal computer, you could do several million elements before you ran out of memory. And so the next step here is to pick some materials. Now, first of all, we need to pick the material that's going to be injected, the molten plastic material. And if we click Change Material, you can see the full plastics database that comes up. This is about there's a library with about 4,500 injection molded plastics in here, everything from ABS to polycarbonates, polypropylenes, EPDM, everything. So let's go to maybe a polypropylene material here. There's also a lot of blends of these materials. And you can see that not only are these materials included, but the specific grade numbers from various manufacturers are specified as well. Let's actually use a PPS for this one, and we'll go with maybe just one of these generic ones at the top. You can see all the properties are included, like the viscosity properties, which are important for how the plastic will flow at different temperatures and what the density of the material is. And that also plugs in what the default temperatures are, the recommended default temperatures are from the vendor of that plastic for what you should inject it at and what the mold should be at. We also can put in some process parameters. How quickly do we want to fill this particular cavity? In other words, how rapidly or what kind of flow rate do we want to push the plastic in at? What the temperatures are, we could tweak those to mimic different process parameters in the real world. And we can put in what the injection pressure limit of the machine is. Of course, we want to know if the machine can actually fill the part, or if it's not able to because the pressures are too high. So we're able to type in the pressure limit of our machine, or we can use this sort of a low-end value as a default, and that will help predict if there's a short shot here or not. And the effect of the insert can be very important here, because as you may be aware, the temperature of the plastic is one of the factors in how easily it flows. And if you've got inserts in the mold which change the temperature of the plastic, it might make it easier to fill a part than you actually thought it was, or it could make it more difficult in other cases. So we can do that, and then lastly we need to specify the injection location. And for a simple part like this, that would be the gate location. I can click that button and either have SOLIDWORKS Plastics give me what it thinks the best gate location is with the automatically add button, although sometimes it will put the gate in a position that's not very practical to manufacture, so we can override that and pick our own location. Maybe I want something at the bottom back end of the part here, and I can simply add that in myself, manually, and I can also select the specific elements that I want to be included in that gate, so that way I can actually plug in the true shape of the gate, whether it's a circular gate or a trapezoid or fan gate, something like that. I could even model a split line feature to make the mesh match that shape exactly. And at this point, we would then click to run at the fill part of the simulation, just the flow of the molten plastic into the cavity. This particular one, because it's a little more complex, would take something like 3 to 4 minutes to complete the fill. But you can see some partial results developing right here as I begin to run it, and we'd be able to see what time we're at in the pressure and temperature of the plastic as it starts to fill up. And by the way, this is running locally on the same computer that I've got SOLIDWORKS open on, and it is multi-threaded. So if you have, let's say, an 8-core Intel processor, that will utilize all of the available CPU cores for the calculation. So anyway, we can terminate the solver here, and we can go look at the finished results for the one that I ran later. Now, once you finish the wizard, there are a couple other setup steps that you may want to go through in the tree on the left. And if you're doing insert overmolding like we are here, the one other key parameter to enter would have been the insert material. So we actually have the ability to specify the material of the inserts and even the material of the mold itself if we were trying to simulate the temperatures in the core and cavity of the mold as well. And so because of that, we have a separate database of metals as well. Of course, you could have a plastic insert, which would let me pick any of the 4,500 plastics that you already saw, or I could choose metal, and there are about 200 metals, most of them aluminum alloys or various steels. And of course, I can pick things like, in this case, a brass 6040 for the connector pins, and that has the specific heat, the thermal conductivity, and the other properties I need to accurately calculate the heat transfer. So if we go to our flow results, the first thing we'd be able to see is whether or not this part was able to fill. And when the solver finished, the first thing that would pop up is what's called the results advisor. And you can see that in this case, it's giving us a message that the part can be filled successfully at quite a low pressure. So we know that most likely we wouldn't have any issues filling this particular part with the material that we selected. We're only at about 10% of what the mold can handle. And so we can see an animation of that fill process, and we can actually look at it in 3D because we've used the solid mesh. We can see what that flow front would look like if, let's say, the mold was invisible here. So it looks like it did fill in the amount of time that we requested, which was about 0.6 seconds. And we can look at everything from weld lines to the pressure or even shear stress in the material and many other properties to evaluate the quality of the part after it comes out and whether or not it's going to have any defects. In terms of insert overmolding, normally the most interesting property to look at would be the temperatures. And so we can look at the temperature at the end of that fill stage, which again is about half a second. We can even look at a cross section here, and we can already see that the cold brass insert, which would have been put into the mold at room temperature, has started to warm up in the area where the hot plastic has been injected around it. And one of the things that we would do is use the measure tool here to take a look at what those temperatures are across the two different materials and maybe what the difference is to figure out whether or not they are starting to bond appropriately or if they may have some difficulties and might be suspect to delamination or debonding later. In this case, there's still quite a large variance at this point because we've just filled the plastic. Now, there are other stages to the injection molding process where you would hold pressure in the mold and then also let the material cool over time. And so we're able to see those results as well. Temperature at end of what we call the packing stage, where you can see now that temperature has sort of equalized a little bit more, and there's only a delta of maybe 50 degrees. And even the post-filling end, and that would be the point at which we're ready to eject the part from the mold, we can see now there's even less of a difference, and there's only really one area over here that's still hot as far as the molten plastic. And the part would probably be more than safe for ejection here. So in addition to all the other properties you might look at, like for example the residual stresses in the material or the pressures, we can look at what those temperatures are to evaluate the effectiveness of the bonding between the insert and the plastic, as well as things like the volumetric shrinkage or warpage, which we'll get to later. Of course, the warp calculation is another capability in the top license of SOLIDWORKS Plastics, which is called SOLIDWORKS Plastics Premium, which could simulate the deformed shape. Now, of course, the question is, what kind of effect could design changes have on some of these parameters and some of these properties? So we've seen that we could look at a cross-section of temperature. In fact, we could even do things like an XY plot, which shows us the temperature at those specific locations over time and what the difference is between them. But what if we want to try to make a change to the design of the part that would speed up this cooling process and maybe help equalize the temperatures even faster between these materials? Well, we're still in SOLIDWORKS, and that's, of course, the benefit of doing the simulation inside SOLIDWORKS here. I can simply go back to my feature tree and change any of the dimensions or maybe add a new feature like a cut and see what that effect is. So here you can see I've put in sort of a chamfered cut extrude to remove some of the material between the pins. So I can simply create that new configuration over here. It's one I've called Improved Cooling. And it simply has this extra feature in the feature tree that you can see down there that I've unsuppressed. And all I would need to do is use that duplicate study capability, and that would copy my whole previous setup to this new version of the model, which I could then mesh and run the same analysis on. So you can see I've remeshed the part in this case so that now this hole is in here. Still got the same gate location. And of course I could go look at all of those same properties like I had before. So here's my pack results. And if I go look at the temperatures at the end of packing, I could see what that cross-section looks like. So you can see there's already less of a gradient there, and there's much less of a sort of hot encapsulated molten area, which is was in the middle before. And I can confirm that at this stage all of the plastic has actually been solidified. You can see it's listed under frozen area. Now, in addition to that, if I want to also confirm that the connector maybe is still going to work afterwards, the pins are going to fit into the female version of this connector, I would need to know what the deformed shape of this part looks like. And so that's where SOLIDWORKS Plastics Premium can come in, which has the ability to simulate not only the heat transfer of the mold itself based on any cooling lines or maybe a bubbler that I would have put into that cutout, but I can also use the residual stress results that I've calculated as part of this cooling process to see how that would warp the part and deform the part as it cools and then is ejected from the mold. And so, of course, that is very important when you want to make sure that the metal insert doesn't also deform or warp out of place, maybe out of tolerance. So I can go to my warp results, and I can see either just the true scale, or in this case, an exaggerated scale of what it would look like, and I can even animate that deformation. Although, again, because this is exaggerated, I can see that the real values are actually pretty low. So the most deformation would be at the back here, where there's no metal reinforcement to the part, and it's still only going to shrink maybe 0.15 millimeters. So I can be reasonably assured in this case, especially if I were to measure the pins, that they're not warping out of position or out of tolerance. Now, the other thing that I might want to know is, if I'm making these changes that affect the manufacturability of the part, what about the operation of the part as well? And of course, that is the benefit of staying inside the SOLIDWORKS interface with all of the other capabilities and simulation tools that SOLIDWORKS has. So for example, if I want to know whether or not I'm going to break the part when I try to pull this connector out of its socket, by bending it to the side or something, I can weigh those results in addition to anything that I've seen from SOLIDWORKS Plastics to make sure that not only is my part going to be manufactured at a high level of quality, but it also will still work in the field when I actually put loads onto it or any other usage situation. So, and that can be combined with everything from the costing tools to maybe some custom tables or spreadsheets that you've created to weigh the pros and cons of all of these changes. But the key is that SOLIDWORKS Plastics gives you some feedback on the manufacturability and how easily and quickly you can manufacture a high quality part, in addition to how well it works once you've made it. And of course, many other parts would be something similar but maybe different materials. And whether or not it's a metal or a plastic insert, SOLIDWORKS Plastics can handle it. You can see here, this is insert overmolding of a toothbrush. That might be like a hard plastic handle with a softer rubber grip, maybe like a TPU material. And again, the heat transfer between those two dissimilar plastics is one of the key things that we need to pay attention to here, as far as whether or not they've bonded. We can even simulate what's called co-injection, which is a different type of overmolding, where there is no insert, and instead you have two different molten materials that get injected into the mold at two different times, and those are done with what you call a valve gate, which opens and closes at different times. So you can specify more than one of those materials that you saw in the database, maybe an ABS plastic for the center and something cheaper or with a better surface finish. And so by timing when the gates turn on and off, we can simulate how those two materials flow together and mix, and whether or not they bond based on their heat transfer as well. And of course, it can help you figure out how quickly you could make that and when to turn on and off the injection of the different materials. So hopefully you've seen that SOLIDWORKS Plastics has some pretty advanced capabilities beyond just the fill of a simple one material part. Of course, if you have any questions, please reach out to your account manager at Hawkridge, or you can always go to the website and simply send us an email, and we can take a look at whether SOLIDWORKS Plastics has the capabilities you need to predict the manufacturability of your products too. Thanks for watching.